The paper titled, From Monomer to Micelle, a facile approach to the multi-step synthesis of block copolymers via inline purification, focuses on the development of a continuous flow strategy for the synthesis of block copolymers and nano-aggregates directly from monomers. The authors highlight the importance of inline purification systems in achieving fully continuous operation and high-throughput synthesis. They introduce an inline dialysis purification system that is significantly faster than conventional batch dialysis, with predictable kinetics and a diffusion velocity coefficient of 4.4 times 10 (-4 s-1). The system uses only 57 ml of solvent per gram of polymer, reducing the required amount by almost an order of magnitude compared to conventional methods. The authors then describe the synthesis of amphiphilic block copolymers using thermal and photoinverter reversible addition fragmentation chain transfer (RAFT) polymerization. They polymerize methyl methacrylate, MMA, or butyl acrylate, BA, as the first block via RAFT polymerization in a traditional flow reactor, followed by inline dialysis purification using a custom-built dialysis device. The clearance of residual monomers is monitored via inline NMR. The authors demonstrate the successful chain extension of the purified polymer in a second reactor stage using poly-ethylene glycol, methyl ether acrylate, PEGMEA, as the second monomer. They also show that nano-aggregates can be created from the flow processes, with a variation in nano-aggregate size from 34 nanometers to 188 nanometers. The paper emphasizes the tunability of the process, allowing for the synthesis of block copolymers with different compositions and the study of compositional influences on nano-aggregate size. The authors also highlight the green chemistry considerations of the method, with significantly reduced solvent waste compared to traditional batch dialysis. In conclusion, the paper presents a novel approach to the synthesis of block copolymers and nano-aggregates using a continuous flow strategy combined with inline purification. The method offers high efficiency, predictability, and reproducibility, making it suitable for automated high-throughput synthesis. It also provides significant advantages in terms of green chemistry, reducing solvent waste. Inline dialysis system design. The first figure in the paper illustrates the design of the inline dialysis system used in this study. The system consists of a dialysis block frame made of 6061 aluminium, with stainless steel fittings and PTFE flow channels. The block is separated by a regenerated cellulose membrane with a pore size of 3 kDa. The system has 2 outlets and 2 inlets for the polymer reaction mixture and the solvent, respectively. The dialysis block enables the removal of residual monomers and other small molecules from the polymer reaction mixture. The design of the system allows for efficient and rapid dialysis, accelerating the purification process compared to conventional batch dialysis methods. Multi-block synthesis platform with inline purification. The second figure in the paper shows the complete multi-block synthesis platform with inline purification. The platform consists of 3 reactor stages. The first stage where a HAMA polymer is synthesized. The second stage where the polymer reaction mixture is purified using the inline dialysis system, and the third stage where block copolymers are obtained without the need for intermediate polymer isolation. The purified reaction mixture can be further chain extended in the third stage using a different monomer. This platform allows for the continuous synthesis of block copolymers and eliminates the need for offline isolation or complete conversion in flow to remove residual monomers. Clearance kinetics by dialysis of PBA and PMMA. The third figure in the paper illustrates the clearance kinetics by dialysis of poly-butyl acrylate, PBA, and poly-methyl methacrylate, PMMA, using the inline dialysis system. The kinetics of monomer removal are monitored using inline NMR spectroscopy. The clearance of residual monomers follows a wavy pattern due to the changing flow rate during dialysis. The kinetics of dialysis are found to be highly predictable, with a diffusion velocity coefficient of 4.5 times 10 (-4 s-1), which is 4 to 5 times faster than conventional batch dialysis. This demonstrates the efficiency and effectiveness of the inline dialysis system for the purification of polymer reaction mixtures. GPC chromatograms for chain extensions of BA and MMA with PEG-MEA. The fourth figure in the paper shows the GPC chromatograms for the chain extensions of butyl acrylate, Ba, and poly-methyl methacrylate, MMA, with poly-ethylene glycol, methyl ether acrylate, PEGMEA. The chain extensions are performed after the purification of the HAMA polymers using the inline dialysis system. The GPC chromatograms demonstrate the successful chain extension of Ba and MMA with PEGMEA, resulting in well-defined block copolymers. The intermediate dispersities observed after block extension are attributed to the inherent chemistry of the block copolymer system or imperfect separation on the SEC system. Figure 5 in the paper describes the clearance kinetics of residual monomers from the dialysis loop. The figure shows the clearance progress of the monomer from the PBADP60 sample, comparing the predicted clearance based on the dialysis velocity coefficient to the measured progress using inline NMR. The data points, markers, closely match the prediction, full line, indicating the high predictability of the dialysis process. The monomer clearance is completed within 6 loops, with each loop taking 25 minutes. This demonstrates the efficiency of the flow dialysis method, which is significantly faster than conventional batch dialysis. The significance of Figure 5 to the paper is that it validates the effectiveness and predictability of the inline dialysis system developed for the synthesis of block copolymers. The faster clearance kinetics of the inline dialysis compared to conventional batch dialysis allows for continuous and high-throughput operation, reducing the disruption in the workflow of block copolymer synthesis. Additionally, the reduced amount of solvent required for purification per gram of polymer is beneficial from a green chemistry perspective. Other figures that are useful to discuss in relation to this paper are Figure 2, which shows the design of the continuous flow dialysis block used in the work, and Figure 3, which illustrates the complete multi-block synthesis platform with inline purification. These figures provide visual representations of the experimental setup and the overall workflow of the block copolymer synthesis process. Figure 6 in the scientific paper shows the GPC chromatograms for the chain extensions of polymers Ba60 and MMA25 with PEG-MEA. The top chromatogram corresponds to the chain extension of Ba60 with PEGMEA, while the bottom chromatogram corresponds to the chain extension of MMA25 with PEG-MEA. The significance of Figure 6 is that it demonstrates the successful chain extension of the HAMA polymers Ba60 and MMA25 with PEG-MEA to form block copolymers. This highlights the potential of the inline purification system described in the paper to enable the synthesis of well-defined block copolymers in a continuous flow setup. The GPC chromatograms show that the chain extensions were successful, as indicated by the presence of peaks corresponding to the block copolymers. This result is important because it shows that the developed setup allows for the efficient synthesis of block copolymers from the monomer stage to nanoparticle formation without the need for intermediate isolation or interruption. It also demonstrates the tunability of the process, as the size of the nano-aggregates can be varied by adjusting the composition of the block copolymers. Other figures that are useful to discuss in relation to Figure 6 are Figure 4 and Figure 5. Figure 4 shows the clearance kinetics of residual monomers via dialysis, demonstrating the effectiveness and predictability of the inline purification system. Figure 5 compares the predicted clearance of the monomer with the measured clearance using inline NMR, further validating the predictive capability of the dialysis system. These figures provide additional evidence of the successful purification process and its efficiency in removing residual monomers. Figure 7 in the scientific paper titled, From Monomer to Micelle, a facile approach to the multi-step synthesis of block copolymers via inline purification, shows the setup of an attachment for the preparation of nano-aggregates. The figure illustrates how the dialysis loop is extended to incorporate a Y micromixer, which allows for the mixing of the diluted polymer mixture with water to induce rapid nano-aggregate formation. This setup enables the formation of various nanostructures, such as spherical micelles, vesicles, or rods, depending on the composition of the block copolymers. The significance of Figure 7 is that it demonstrates the capability of the developed continuous flow system to not only synthesize block copolymers but also produce nano-aggregates in a single setup without the need for intermediate isolation or interruption. The attachment shown in Figure 7 provides a platform for studying the effects of block copolymer nature, composition, and length on nano-aggregate formation. This allows for high-throughput studies and investigation of nanostructure counterparts based on different block lengths and compositions. The results obtained from this setup provide a foundation for further exploration of block copolymer self-assembly and its applications. It is worth noting that the paper also includes several other figures that are relevant to the discussion, such as Figure 4, which shows the clearance kinetics of residual monomers via dialysis, and Figure 6, which presents GPC chromatograms of the chain extensions of different block copolymers. These figures contribute to the overall understanding of the continuous flow synthesis and purification process for block copolymers. This paper presents a novel approach to the synthesis of block copolymers via inline purification. The authors developed an inline dialysis purification system that is significantly faster and more efficient than conventional batch dialysis methods. The system was used to synthesize amphiphilic block copolymers from thermal and photoinverter reversible addition fragmentation chain transfer, RAFT, polymerization. The purified reaction mixture was then used for chain extension and the formation of nano-aggregates. The authors demonstrated that the inline dialysis system is highly predictable and uses significantly less solvent compared to conventional methods. They also showed that the system allows for the synthesis of block copolymers and nano-aggregates in a single setup, without the need for intermediate polymer isolation. The approach has the potential to accelerate the synthesis of block copolymers and enable high-throughput studies of nano-aggregate formation. The authors also highlight the green chemistry benefits of their method, as it reduces solvent waste compared to traditional dialysis methods. Overall, this study presents a promising strategy for the efficient synthesis of block copolymers. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.